In section 2.1, we introduced the idea of symmetry of functions. We're going to just explore that some more here in section 2.2, and then talk about behavior of functions, piecewise functions, and our difference quotient. Remember that we focused on even and odd functions. We only have one test of symmetry. Now, there are multiple tests for symmetry, and there are different types of symmetry, but for our purposes this semester, we're going to stick with a single symmetry test that will give us one of three results. Either we have an even function, we have an odd function, or it's neither one of those two. If you have an even function, the function will be symmetric about the y-axis. That means that if you had a graph and you folded it along the y-axis, both of the sides would match up. For example, a basic even function graph is our quadratic function, where if we start with f of x equals x squared, and I do my symmetry test of plugging in a negative x, then I square that, I get out the same thing that I had originally. So an even function, when I plug in negative x, nothing changes. I get out the same thing I started with when I just had positive x. Another example of an even function would be, let's say g of x equals x squared plus 5. Because when I plug in a negative x here, after I square that, nothing changes. So I have an even function. When nothing changes, when I plug in a negative x, I get out the same as what I started with. Nothing changes. I have an even function, and the graph of that function will be symmetric about the y-axis. With an odd function is going to be symmetric about the origin. Remember, it has that twist in the middle. So my basic example for an odd function was our cubic function, remember. There's a cubic function. The sides are supposed to match. I'm not great with my free-handed graphs, so you guys need to have a little bit of grace with my lines that are supposed to be straight, with my graphs that are supposed to be balanced. I need you to have a little bit of grace with me this semester. So with an odd function, when I plug in that negative x, what happens is I get out the opposite of what I started with. So you see here I have a negative x cubed instead of a positive x cubed. For an even function, when I plug in a negative x, nothing changes. They come out the same. For an odd function, when I plug in a negative x, I get the opposite of what I started with. Everything changes. So for an odd function, when I plug in negative x, I get out the opposite of the original function value. So for example, if I plugged in 2 and got out, so here if I plug in 2, I get out 8. If I plug in negative 2, I get out negative 8. When I change the sign of the x, it changes the sign of the y. Now, if I plug in a negative x, and some things change but some things don't, that tells me it's neither even nor odd. But that doesn't say that it has no symmetry. What that says is that we have no predictable symmetry, at least not according to this test, which is the one we're interested in. No predictable symmetry. So, for example, let's say we have f of x equals x to the 4th minus 7x cubed. That's my function, and I want to know if that function is even or odd or neither. Well, the way I check to see is I plug in a negative x. So anywhere I have an x, I make it a negative x. I have two terms in this function. For the first term, the exponent is even. That means I'm multiplying a negative times itself 4 times. Well, those negatives are going to pair up 2 and 2, so that it ends up being positive. This term, negative x to the fourth power, is just x to the fourth. But for the second term, my exponent is odd. So I'm multiplying a negative times itself 3 times. Well, 2 of those negatives are going to pair up and become positive, but I've still got that one negative left over. So a negative x cubed is a negative x cubed, which gives me negative x cubed times negative 7, which is a positive 7x cubed. So this is what I get out. Well, when I compare this to the original, I see that the first term stayed the same, but the second term changed sign. If one or more terms stay the same and one or more terms change sign, so it's not all the same or all the opposite, then we can say, we just don't know. Has no predictable symmetry. Let's practice this a little bit. It says to determine whether the given function is even, odd, or neither, and then tell what type of symmetry it has. Well, my symmetry test is to plug in a negative x. So for this first one, f of x, I would find f of negative x. So I've got negative x cubed plus negative x. Notice that these are both odd exponents. Here it's just x, which is the same thing as x to the first. 3 is odd, 1 is odd. That means this first term changes sign to negative x cubed, and the second term is now minus x, which if I factored that negative out is the opposite of what I started with. So everything changed. When everything changes, we have an odd function. And odd functions are symmetric about the origin, so it has origin symmetry. Let's look at the next one. I want to make note on g of x that my first exponent is even and my second exponent is odd. That causes me to pause. It doesn't, when I have an even and an odd exponent, that means that I probably am not going to get a helpful result. So let's plug in our negative x to see what happens arithmetically. That's a negative x squared. Sorry that I jumbled that a little bit. And then plus a negative x. Well, for the squared term, those negatives pair up and nothing changes. So that's still x squared. But for the x term, the sign changes. So I had one term stay the same and one term change sign from the original. When one changes, one stays the same, I have no predictable symmetry. It is neither even nor odd. Neither, and there is no predictable symmetry. So let's look at that last one. H of x. As I evaluate it to start with, I see that I have 2 even exponents. That's promising. Even exponents ought to lead me to an even function. So if I plug in h of negative x, then I have negative x squared minus negative x to the fourth. And these two negatives are going to pair up, and that doesn't change. These 4 negatives all pair up, so that doesn't change. And I get out the same thing that I started with. Nothing changed. When nothing changes, I have an even function, and that gives me y-axis symmetry. I could take the graph, fold it along the y-axis. What this means for me is if I know what one half of the graph looks like, I can just reflect it across that y-axis, and I know exactly what the other half of the graph will look like. Okay, let's step away from symmetry and talk about behavior of functions. There's some basic rules of behavior of functions. We need to discuss intervals where the function is increasing, decreasing, and constant. Now, when we're interested in these intervals, we're interested in reading a graph and explaining what the graph is doing. When I'm reading a graph, I want to read it along the x-axis from left to right, just like I'm reading a book. And then the behavior that I'm talking about should describe what the value of the y value is doing, what the function value is doing as I move from left to right. So as I move from left to right, is my function increasing? Is it going up? Is it going down? Or is it being constant? Is it flat? So I'm moving from left to right, but I'm talking about what the y value is doing, up, down, or constant. When I give the interval, I'm giving the interval on the x-axis at which that behavior happens. I also am interested a lot of the time in identifying any relative maxima or relative minima that occur in the graph. These are my peaks and valleys, my highs and lows. Where does the graph take a turn? It may not be the absolute highest point on the graph, but it is a high point. Okay, let's look at the next page and talk about the behavior of this graph. And then we're going to do one of those practice problems, and I will save the other one for you to work on your own. For these practice problems, if you are in one of my classes that meets together online, then we will go over those practice problems at that time. If not, and you would like to get a key to this practice problem, if you're in a Connect class, you can always email me and I can help you check those keys to see how you did. All right, so when we are describing the behavior of a graph, we have two questions. We're looking to see we have one main question. What, and I said why, what is y doing? What is my y value doing? D-O-I-N-G. What is my y value doing? That's the question I'm asking. Now, when I give the answer, I'm going to give the answer based on the interval on the x-axis. So when I give the answer and I say y is increasing, well, I tell you where that is happening on the x-axis. For example, right here, as I read across this graph, and I'm going to go ahead and outline my graph in blue. I like to use color if you have not noticed already. This is the graph that I'm interested in right here. And you see we just have a piece of it because it's got arrows on both ends. So we know it continues moving on. Well, if I start over here at negative infinity on the x-axis and I am moving in a positive direction from left to right, I see that this y value, the arrow is pointing down, but that just means it's coming from down here. The graph, as I move from left to right, the graph, the y value is increasing. And it is increasing from all the way over here until this point when it stops increasing. So the interval on which this function is increasing is the interval on the x-axis from negative infinity until I get to -4. Now at -4, this is a turning point. It's no longer increasing here. It is changing from increasing to decreasing in this case. Because of that, this book chooses not to ever include those endpoints. It always uses parentheses, not square brackets, when we are talking about intervals where the graph is increasing, decreasing, or constant. Other editors and other books may address this differently, but for our purposes in this book this semester, we're going to use these parentheses, and I really like that because -4 is a point of change. It's not increasing here, it's not decreasing here, it is changing, it's turning here. So it turns, right? When it turns, now my graph is decreasing. You can see that as I keep moving left to right, I've been moving on my x-axis. I stopped at -4 because I had a turning point. I was increasing, it turned. Now the graph, the y value, the function value is decreasing. And I see that that graph is falling, it is decreasing until I get right here. And when I get right here, where x is 0, the graph now levels off. So that is another change. So I have an interval where the graph is decreasing from -4 to 0. That's the interval on the x-axis. The behavior that is described is decreasing function value. Once I get to 0, we said it makes a change again. That change is that it levels off. My function value is level, it is constant. As I move from left to right along the x-axis from the x value 0 to 4. The graph is constant, the function value is constant on the interval from 0 to 4. Now again, these intervals are the place on the x-axis. They're not giving me function values. The word describes what the function value is doing. At x is 4, I have a turn again, and my function starts increasing. That function continues to increase on the interval from 4 to 6. When x is 6, it turns again. So on the interval from 4 to 6, I am increasing. And then it turns, and I decrease for the remainder of the life of the function. Now, I end in an arrow. That means it just keeps going forever and ever and ever. So my function is decreasing from 6 to positive infinity. That's the interval over which it is decreasing. The function value is heading to negative infinity. The interval on what that is, over which that is happening, is 6 to positive infinity on the x-axis. Okay. Let's work through this first practice problem down here on the left. And again, I'm not going to do the second one with you. I'm going to leave it for you to work with, or if we are doing an online class that uses BBCU, we will talk about it there. Okay, we have several questions about this graph. Hopefully you can see your graph has an arrow here. And we've got a constant function, and then we have this parabolic piece that ends in an arrow there. That's my function f of x. The first question, what is the domain of f? What's the domain of my function? Well, since I have arrows going both directions, my domain is going to be all real numbers. The range of the function, I always go least to greatest. I go least to greatest left to right for the domain. I go least to greatest bottom to top for the range. So I start down here at y is negative infinity. I work my way up, and I see my function starts right here at that y value negative 4. Now, as I travel up, if I look back to the left, I have a constant function that levels off. But if I look over to the right, I see that my function keeps going forever in a positive direction. So my range is going to be from negative 4 inclusive to positive infinity. Then I'm interested in x and y intercepts. Remember, my intercepts happen where I intercept or run into the axes. The x-intercepts happen where I run into the x-axis. For that to happen, y has to be 0. And I can look at my graph and see that I run into the x-axis in 2 places. At x is 1 and at x is 7. So those 2 ordered pairs give me my x-intercepts. If I have a function, I only ever have one y-intercept. It happens when x is 0. And I can see on my graph that my y-intercept, where x is 0, y is 4. That's the value of my y-intercept. Now we're going to talk about those intervals over which the graph is increasing, decreasing, and constant. We're giving intervals on the x-axis describing what the function value is doing. So where is my function increasing? Increasing means it's moving upward. Well, I see that right here, my function is at a low point, and this is a turning point, and then it keeps moving up for the rest of the function. Now, I don't go left or right. I'm always thinking about moving like I'm reading a book from left to right. So I've got constant, decreasing, and then it turns and is increasing for the remainder of the function. So where x is 4, I have that turn, and then from then on, the function is increasing. So my function is increasing over the interval 4 to infinity. Where is the function decreasing? Well, again, I read my function from left to right. My function is constant all the way until I get to 0, where x is 0. And then at that point, it drops and it decreases until I get to this x coordinate of 4. So over this interval from 0 to 4 is where my function is decreasing. Where is my function constant? Well, this piece is constant. all the way out this direction. So as I move from negative infinity this way, my function is constant until I get to the x value 0, and that's when it takes a turn. So it's constant from negative infinity until 0 on the x-axis. H asked me the question, what is the number at which my function has a relative minimum? And then I says, what is the relative minimum? So the location is the x-coordinate, the value is the y-coordinate. Well, this is my relative minimum. This is that low turning point. You can see I've got this valley here. The relative minimum occurs at x equals 4, and the value of that relative minimum is down here at -4. That's the y value of that relative minimum. Then we're asked for a specific function value. What's the value of the function at -3? Well, let's go find out. X is -3 here. I go up and intercept the function at 4. What is the value of x, or values of x, for which the function value f of x is -2? Let's go see. Well, a function value f of x is my y value. Y is -2. That happens here and there. So that happens at the x coordinates 2 and 6. And then finally I'm asked, is this function even, odd, or neither? Well, I'm not given an equation, so I can't plug in a negative x. I just have to judge looking at the graph. Does it reflect across the y-axis? Can I fold it on the y-axis? Well, absolutely not. Does it have a twist in the middle? Does it center on the origin so that one side's up and the other's down? Well, no. So it does not have any predictable symmetry. It is neither even nor odd. All right, let's look at the next page. On this next page, we move on to piecewise functions, piecewise defined functions. Piecewise functions are functions where there are different rules that define different regions of the domain. So that it looks like the function is pieced together. We have different rules for different pieces of the function. My most basic piecewise function is my absolute value function, f of x equals absolute value of x. So we're going to think about this in terms of graphing the function. Hopefully some of you go, oh yeah, I know what that looks like. The absolute value function, the shape is a V. And this is my parent absolute value function. So we know what to expect from our graph. But let's write it as a piecewise defined function. If I write it as a piecewise defined function, I know that my function value is going to be equal to x for all x values that are greater than or equal to 0. And I know my function value is going to be the opposite of x for all x values that are less than 0. Now, the first thing I want you to notice about a piecewise defined function is that I have split the domain at 0, but for this particular function, I did not leave 0 out. 0 is included in this first piece of the function. Now, we don't do a lot of plotting points and creating coordinate pair charts, but we're going to do it for our piecewise defined functions to help us structure them. So this first piece is for x values greater than or equal to 0. That's on this right side of my y-axis for my positive x values. So I'm going to do my chart over here. I'm going to say for x values greater than or equal to 0, my function f of x is just equal to x. So my boundary is 0. I need to include that. And then I want values greater than 0. I don't need to do a lot of them. I'm going to choose to do 1, and I'm going to choose to do 1, 2, 3. Let's do 4. That fits on my graph. And then my rule is I plug in x, I get out x. So for x is 0, y is 0. For x is 1, y is 1. For x is 4, y is 4. And it would just keep going. This is just some points for me to plot. I get to include this point because 0 is included. So I'm going to say, okay, 0, 0, I've got 1, 1, I've got 4, 4, and I know that I get to keep going because I get to have increasing x values. Now let's look at the other piece of this function. the piece of the function for which my domain is less than 0. That is this piece of the function where my domain is negative x values. So let's set up our chart. For x values less than 0, not inclusive, f of x is equal to negative x. So let's pick some x values that fit here. Now I need to include 0 because I need to go there, but it's not included, so it's going to be an open circle. So I'm going to do a little kind of a Campbell, look at this squiggle. This reminds me that I'm going to go there. It's going to be an open circle. It's not going to be filled in because I go up to that point, but I don't include it. Then I need some negative x values. I did positive 1 and positive 4. Let's do negative 1 and negative 4 here. So if I plug in 0 for x, I get negative 0. That's not a thing. 0 is neutral. If I plug in negative 1, I have the opposite of negative 1, which is positive 1. If I plug in negative 4, I have the opposite of negative 4, which is positive 4. So let's graph these points. Because I go to 0 but don't include it, at 0, 0, I need an open circle. It was closed and included for this piece of the function. It's not included for this piece of the function. I have the point negative 1, 1, and I have the point negative 4, positive 4. I know I would keep going because that's the way my domain is set up. So there's the graph of this piecewise defined function. All right. We are going to do, you know what? We are going to do one more example of these, and I think we're going to do g of x. For g of x right here, this is the one we're going to do the example of. We're going to do this piecewise defined function together. G of x is divided into two pieces, and my first piece is given the rule negative 3. So that's just a constant. And it's for the domain values x less than 0. The second piece is given the value 2x plus 4. That's a linear function. If I graph this, the graph is going to be a line, and I see that my coefficient on x is positive, so my line is going to have a positive slope. So I already know some things about what the shape of this graph is going to be. This is for x values greater than 0. I want you to notice that 0 is not included in either piece. So my domain leaves 0 out. It's not all real numbers. For the function I did up here, my domain was all real numbers because even though I split the domain at 0, it was included in one of the pieces. Once I got the graph done, I could see that the range is from 0 to positive infinity with 0 inclusive. For g of x that we're graphing here, I see that my domain is not all real numbers because I have left out 0. My domain is everything from negative infinity up to 0 or 0 to positive infinity. That's how I write my domain as an interval. I can't do my range until after I get my function graphed. I need to see it before I can figure out what the range of the function is going to be. All right, let's look at this first piece of the function. This piece of the function is for all x values less than 0. So for x values less than 0, my rule is that no matter what I plug in, the answer, the y value, is negative 3. Okay, I know I need to include 0 on my list, but it's not going to be a filled-in circle. It's going to be an open circle. I go up to that point or down to that point, but I don't include it. I need a couple more values in here. Let's do, I don't know, let's do just negative 1 and negative 2. That's negative 1 and negative 2. There we go. So no matter what I plug in for x, it comes out as negative 3. That is a constant function. Let's go ahead and graph that. I go to x is 0, and at x is 0, y is negative 3. Oh, you know what? We're going to do something here with my axes. I'm looking at my completed graph on my notes, and I see that if I do it the way it is, we're going to be kind of off the chart. So we're going to count by 2s on our axes just so that everything fits on our graph better, okay? So I want to challenge you guys to go in and to count by 2s on your axes so that when I graph this, everything fits where I want it to fit. So where x is 0, y is -3, which is going to be halfway between -2 and -4. So right there, -3. And this is true for all of my x values that are less than 0. Got an open circle here because it's not included. It just goes up to that point. Now, here's the problem if I started at -1. If I had started my graph at -1, or right here at -1, I would have this gap here. Remember that graphs are not only integers, they include decimals. So we've got to include everything between -1 and 0. All right, let's look at our second rule. My second rule is for the x values greater than 0. And that rule says g of x is 2x plus 4 for those x values. Again, I need to think about what 0 would be, even though it's not going to be a filled-in circle. And then I need to pick some positive x values. I did -1 and -2. I'm going to go ahead and just do +1 and +2 and see what I get. So if I plug in 0, I get 2 times 0 is 0 plus 4. If I plug in 1, 2 times 1 is 2 plus 4 is 6. And if I plug in 2, 2 times 2 is 4 plus 4 is 8. And these values are why we counted by 2s, because I knew what my result was going to be. All right, 0, 4 is going to be open. So at 0, 4, I have an open circle because it's not included in this piece. Then I have the point 1, 6. So at 1, I'm up to 6. And at 2, I'm up to 8. So I have this really steep positive linear function that goes up just like that. Okay, let's talk about range now that we have our function graphed. Our domain was everything but 0. Let's read our range, reading down here from -infinity and moving up. Well, I see I have a single value at -3 and then nothing until I get up here to 4. So when I write my range, I write that single value at -3 in fancy braces, and then it picks up at 4, and 4 is not included, so parentheses, and it keeps going up forever, positive infinity. Okay, that's our example of a piecewise defined function. Let's talk about difference quotient. When we find the difference quotient gives us the average rate of change between 2 points. If I had a straight line, like this right here, it would have a slope. I would know that no matter where I am on the line between any 2 points, it has the same rate of increase or decrease. If my graph is not a straight line though, for example, this curve, the rate of change depends on which 2 points I'm looking at. For example, right here, if I pick these 2 points, I have a negative rate of change right here. I'm going down. Here it's kind of flattened out, more flat. Here it's increasing more steeply, increasing more steeply. So if I have a curve, I do not have a slope, but I can talk in terms of an average rate of change. Now that average rate of change is going to be determined by what 2 points on the graph I pick. And it's given by the equation f of x plus h minus f of x over h. And here is where those terms come from. Think about how we find slope for a line. If I'm finding slope for a line, I talk about change in y over change in x. Well, my x coordinate is from here to here. That's my distance on the x. That h is how far over I move from the first point to the second point. That's my denominator. Difference in the x coordinates is h. My difference in the y coordinates, my numerator, I'm going to think about starting with this second point. If I have moved over, that's that y value, minus this original y value. The y value of the second point minus the y value of the first point. So f of x plus h minus f of x divided by the change in x, how far apart the x coordinates are. This general form is going to give me the average rate of change for any formula depending on what x value I start with and how far over I move. We're going to do a couple of these together, and then we're going to leave and let you practice it later. Now, the first thing I want to point out is that my first example is a line. 3x plus 2, that's a linear equation. Well, the slope of a line is constant. It is going to be a constant 3 here. We know that, so we know what we're expecting. But we're going to practice using our difference quotient with this simple equation so that you can ease into it. My difference quotient has 3 pieces. I have f of my function of x plus h. So I'm going to plug in x plus h everywhere there's an x. Then I subtract the original function right here, and I put that all over h. So let's go ahead and set it up as something over h. Well, the first piece is this f of x plus h. So I take my function, and where there is an x, I replace it with x plus h. So that would be 3 times x plus h plus 2. That's this first piece. And then I subtract from that the original function. Well, here's my original function, 3x plus 2. Those parentheses are very important because I'm subtracting that entire thing. That's all over h. This is how I find my difference quotient. So let's do that. Let's do a little work here. We've got it all over h. For this first piece, f of x plus h in green, I first need to distribute so that I have 3x plus 3h, and then I have plus 2. For the second piece, the minus original function, minus 3x plus 2, I have to distribute this negative inside the parentheses. So minus 3x minus 2. Again, I'm still all over h. So let's see what we get next. Well, I want to pair up any like terms. I notice that I have 3x and negative 3x. They add to 0. So that adds to 0. Then I have 2 and negative 2, and that adds to 0. What I'm left with in the numerator is just 3h. And h over h, anything over itself is 1, so it cancels out and leaves me with a slope of 3. That's exactly what I was expecting for that line, a nice integer slope. Okay, let's do number 2 example together. Is this the graph of a line? If I were to graph this function, would it give me a line? Hopefully you recognize that is a quadratic function. And a quadratic function does not have a slope. It has a curve, right? So it has one part of it is going to be decreasing, the other part is increasing, and at different rates. So we know when we use our difference quotient, it is not going to come out with a nice integer result. We're going to have something that's not just this nice integer result. So let's start with our setup, our formula. We know we've got a bunch of stuff over h. The first thing we're told to do in our difference quotient is to take our function, h of x in this case, and anywhere there's an x, I replace it with x plus h. So right here, this is x plus h quantity squared, and here I have minus 2 times x plus h. That's the first piece of my difference quotient. The second piece of my difference quotient is to subtract this original function. So I have to put it in parentheses. Minus x squared minus 2x. Okay, just like we did last time, we're going to go in here and we're going to start simplifying some things. I know it's going to be all over h, so I set that up. For this very first binomial squared, that's going to give me a trinomial, a perfect square trinomial. You either need to do that off to the side, x plus h times x plus h. We can come up here and say x plus h times x plus h and FOIL that. Or you can use your shortcut. Square the first term, multiply them together times 2. square the second term. These three terms are what you get if you used your shortcut or if you come over to the side and you FOIL. The next thing I need to do is going to be to distribute this -2 inside my set of parentheses here. So minus 2x minus 2h. I'm going to need a little bit more space in my numerator. Next, I need to distribute the negative inside that set of parentheses. So minus x squared plus 2x. Next step, I'm going to combine like terms in my numerator. I'm always going to find pairs of opposites. Positive x squared and negative x squared add to 0. Positive 2x and negative 2x add to 0. That's it. So what I'm left with then is 2hx plus h squared minus 2h all over h. Well, I see that in my numerator each term has an h. So I'm going to factor that common factor, that h, out of my numerator. That would leave me with 2x plus h minus 2. And then because h over h is 1, my result for this difference quotient is 2x plus h minus 2. This gives me my average rate of change on this parabola for this function, starting at any given x and moving over h units.